What I'm going to talk to you today is what the slide says, communications. But in order to understand or make sense of communications as they are now, you've got to know how it was done in the past. So this is going to be a little bit of a radio lesson. So Anne will be just fine. She'll just cruise this. She don't have any trouble. You'll all pass a foundation amateur radio exam by the time you've seen this, assuming you've absorbed it. Okay, what's that?
Spacecraft?
No. All right, so that's not what that's about. Okay, the way it's all been done, always been done. When radios first were used, they were essentially a series of single components all working together. Not very many of them, just enough to be able to resonate, to produce an HF, to produce radio frequency communications, radio frequency signals, and either to transmit or to receive them. But the trick, once they got over the original problem, working out how to split the frequencies off, so that the initial radios were spark gap, that was just all the frequencies, everything, there were no channels. We had to find a way to pick individual frequencies out of the air, and there are lots and lots of radio signals coming at you all the time, all right? Now, the solution to this was the tuned circuit, which is a circuit that responds to one frequency by increasing what's known as the impedance. Now, impedance is kind of like electrical resistance for alternating current. What you think of as electrical resistance is normally only applied to direct current, and that causes heating. But alternating current also experiences resistance, but it's a more complex situation because it depends on interactions between various of the components in the circuitry. I'll see that in a moment. The circuit becomes tunable when you can vary the quantities in the components in the circuit. Right? So then you can pick a frequency, you can change channels. So this is a really basic circuit diagram for a radio. And the bit that really matters is this bit just here. Okay, that's the guts. The what?
You should point her on.
Yeah, I think we're probably.
No. Well, your cursor to point because the people at home can't see where you're pointing.
Okay, I can't do that here.
Oh, okay.
Right. All right. So what we're looking at there is a basic radio circuit. I'll explain to you what the components are. You see in the top left, there's a funny little triangle arrangement, upside down triangle. That's your antenna. The bit at the bottom is called the earth or the ground. Simple enough. The bit on the left is marked L is an inductor. That's just a coil of wire, or sometimes with a coil of wire with something through the middle of it. The thing that's marked C1 is a capacitor. That's just two plates facing one another at different voltages. The inductor, L, stores energy in a magnetic field. The capacitor, C1, stores energy in an electric field. As you charge the capacitor up, the voltage builds up and pushes the current back to L. Then the magnetic field builds up in L, and the impedance of that part builds up and pushes the current back to C. So it oscillates backwards. It's a resonance circuit. When that happens, depending on those component values, there is a frequency which that naturally resonates at. When that happens, that frequency is kind of held in the resonance section of the circuit between the capacitor and the inductor, and all other frequencies are allowed to bleed through to Earth. So now you've picked one frequency out of a whole range of frequencies that might hit the antenna. Because that oscillation is occurring across the capacitor there, that is made available to the rest of the circuitry. And the rest of the circuitry then splits off the alternating current, the high-speed alternating current using the transistor. That Q object there is a transistor. That's one transistor. That's all it is. And the output voltage then is the high-frequency component of that signal is bled down to Earth, and the low-frequency component, which is probably a voice or something being turned on and off, gets through to the terminal just near the speaker, and you hear the sound. That's really all there is to it. But the real key to it is that resonance circuit, the L and the C1. So that's the basics of it. Right, so that was how it was done. You recorded a voltage, you developed a voltage. Right, now what happens is we develop a voltage and we store that voltage as a series of numbers. We digitize it. And we digitize it at a certain rate. And you see there that there's an interval between points, and that's called T, that's the period. The inverse of that is the frequency of the digitization of the sampling, is the correct term. Right. So it's turned, that nice smooth voltage curve you see there is turned into a series of discrete numbers, and this is considered an acceptable record of the signal. This is the little slightly complicated bit. As long as the sampling rate, the rate at which you sample the signal, is at least greater than twice the bandwidth of the signal. So if the bandwidth is 10 kilohertz, you would want a signal faster than 20 kilohertz. In fact, considerably faster than that. This is known as the Nyquist limit. And it's something we live and die on with digitization. Right. Now, sorry about this, as I know it's a fantastically complex looking diagram, but I want to make the point that what we're dealing with now is what's called a software-defined radio, which is essentially this little gadget you see here, which I pinched from Eva's lab. Okay, I didn't ask Eva, I just pinched it. I'm going to give it back. So now, that little thing is the software-defined radio, or is considered to be the software-defined radio. In particular, the little silver arrangement in there is an array of logic gates and AND gates, or exclusive OR gates, and they switch very quickly. They can now receive that signal at each of that points because you can get it to switch for each of the times you need it to receive the signal. Okay. The first bit of that, the top of that, there are two diagrams there. The first bit is the control. You receive the signal, that's that RF hardware you saw earlier on, and the antenna is on the left. You turn it into a digital signal, you sample it. That's the digital to analog to digital converter, ADC. You channelize it, you do a lot of software stuff to it, and then you process it. We don't need to go into all the gory details here because we'll be here all night. So that's the basic four parts: the radio frequency, intermediate frequency, analog to digital conversion, the digital front end, and what's known as the baseband processing. The baseband processing, the digital front end, and the analog to digital conversion is all done in a computer. And if you look at the signal at the bottom, there's a waveform through various blocks, and it's split up into two parts: hardware and software. Okay, the bottom, just the bottom line there indicates the bit of this process that is controlled in software and the bit that's controlled in hardware. And that's why it's called a software-defined radio, because most of the work is done in the computer by the software. That's why I showed you that diagram. You don't need to know the gory details. Okay, so now we're dealing with digital signals. What are we going to do next? We're going to actually receive the signal from a moving spacecraft. This is spacecraft communication. All right, the spacecraft is moving, obviously. If it doesn't move, it falls out of the sky. Then it really does move, and then it burns up. It's moving in low Earth orbit of order 7,500, 7,600, 7,700 meters per second. So that's nearly 5 miles a second. They're fairly hoots, right? All right. The frequency appears to alter as we receive it. And the spacecraft appears to seize a different frequency because of its movement. When it comes over the horizon at us, it's moving towards us at a considerable speed, and depending on the frequency that you're transmitting to it and the frequency that it's transmitting, that variation could be as much as 11 kilohertz in the bands that we're on. That takes you out of channel, out of band. That means you can't hear the signal anymore. So you have to compensate for it. And this is called the Doppler shift. And it's one of the most important parts of spacecraft communication. So it's a simple enough equation. The frequency of the ground station is the velocity of the mobile ground station it's moving divided by the wavelength times sine theta, sine phi cos theta. That's just the angles to the spacecraft. You don't need to go into the details about that. And the frequency from the satellite's point of view is the same, but just with the relative change in frequencies. It doesn't have to track you, you have to track it. You do the work on the ground. You don't let the spacecraft do the work because that uses resources which you don't want to use. If you can put a resource on the ground, you do that because it's more efficient. You've got more work, more payload that way. Here, lambda c is the wavelength of the carrier. That's the radio frequency signal. So if I say we're talking at 400 megahertz, that's the lambda c. 400 megahertz is the inverse of that. It's the wavelength. Vmob is the speed of the mobile ground station. Normally that's 0 with respect to the ground, but of course the Earth is rotating too, so it is moving. The elevation and azimuth angle, that's just where you point the antenna. And vrel sat is the speed of the spacecraft relative to us on the ground. As I said before, that is about 7,500 to 8,000 meters a second, so very fast. All right. Now, waves emitted from a stationary object. I hope you can all see this bit. When wave is emitted from a stationary object, the wavelength is the same in every direction. Okay, simple enough. But when it appears from an object that appears to be moving, this is how it appears to a stationary observer. What you see is the waves in front of that object bunch up together. So the apparent frequency we see viewing as it approaches us is much higher than the actual frequency it's transmitting at. And in recession, if you look at it from behind, we see a much lower frequency by exactly the same amount. Okay? And we have to compensate for that in real time as we talk to the spacecraft. So we compensate for the Doppler shift. This is all done in the computer. And the signal varies, the frequency varies as you see there. This is for a spacecraft at an altitude of 750 kilometers, a little bit higher than the university runs out. You can see that if you're dealing with about 430 odd megahertz, the variation is plus or minus about 11 kilohertz, 10 or 11 kilohertz. If you're dealing with a 2 meter signal, that's 144 megahertz, the variation is of order about 3 kilohertz maximum either way. That's not too much. You can deliver that pretty easily. But if you're dealing up at 2.4 gigahertz, which is a lot of spacecraft communications at that frequency, that's the S-band. I think S-band, yes. That variation is up to 60 kilohertz. That takes you way out of band that you record. And so you really have to pay a lot of attention to it, to work hard to keep the thing hearing you, so you can continue to hear the spacecraft that it can continue to hear you. Because you have to compensate when you transmit in the opposite sense that you compensate when you listen. As the spacecraft approaches you, you have to turn your frequency up. When you transmit, you have to turn your frequency down so that the spacecraft hears the correct frequency as it's coming towards you. So all this has to happen in real time. Signal loss. Okay. Now, this is a little bit involved, but I'll just go through a loop budget. A loop budget is something we always do when we design a comms link with the satellite. We look at all of the places where we lose signal from the spacecraft to the ground. There's quite a few. And that's the equation. Sorry, it's a little bit involved, but it's just a bunch of signals added up. And we're dealing now in decibels, which is a logarithmic intensity, a relative logarithmic intensity. And I'll go through each one of those characteristics. You have a received signal power on the left-hand side. Okay, that's what we want to calculate. We need to know the transmitted power, or from the spacecraft, from these small satellites, it's more than 1 or 2 watts. It's not very much at all. The transmitter has an antenna, obviously. We want to know how much gain that has. The gain is the apparent increase in signal because of the directionality of the antenna. There's a few transmitter ancillary losses, and that's losses in connectors and cables and so on. So we have to take that into account. It's a huge, great spreadsheet, massively complex thing. The loss through free space path attenuation. That's the biggest loss of all. The spacecraft is a long way away when you communicate with it, and the signal has to get to you, and as it does so, it sprays out into space, and you lose most of it, and you lose an enormous amount. Okay, we'll talk about that in a second. Then there's miscellaneous losses in on the ground, and the receiver gain that adds to the signal. The receiver gain is the directionality of the antenna on the ground. Usually that's very high, so you gain a lot of strength from that. And then the receiver ancillary losses, once again, cables, connectors, so on and so forth. All right. Most of the loss is in free space, as I said. The largest single loss is distance, and this is for a called free space path attenuation. The signal loss is measured in decibels, which is 1/10 of a bell, after Alexander Graham, and it's just equal to that equation you see there. Log of the power transmitted divided by the power received. It's a ratio, and you multiply it by 10 because you want to take 1/10 of it. So it's just a logarithmic signal. Then the whole thing put together, all of those signals put together, losses and gains put together, is referred to as the Friis equation. Spelled F-R-I-I-S, named after Harold Friis, who was a Danish-American engineer that came up with stuff. And that takes care of a lot of other things too, like the relative size of the antenna. Smaller and higher frequency antennas are physically smaller, so they intercept less radiation. All that's taken care of with this. All right, distance. Sorry, one more. This is the last equation. There's a section of Earth. You've got an antenna at the top there, that's your ground station. You've got a spacecraft traveling on that little dotted track above Earth. The distance between the antenna and the ground and the center of the Earth is just the radius of the Earth. The distance between the radius of the Earth, the center of the Earth, and the spacecraft is the radius of the Earth plus the height of the orbit. It's the two numbers you need to have. Plug it into that equation there. And what you get is, oops, sorry. At a distance, at an altitude of 400 kilometers, it's nearly 2,300 kilometers to the spacecraft. So most of the distance across Australia. That's a pretty fair distance in free space. And you lose a lot of signal in that distance. If you plug it into that equation, the free space path loss is a little under 153 decibels. How much less is that? It's that many times less. It's 1,000 million times less. And yet we hear it easily. The sensitivity of this circuitry you see here is incredible. We hear it easily. The Voyager spacecraft loss is over 300 decibels. And I can't fit the number on the screen. It's just so
And we're still talking to it.
And we're still talking to it. Not at a very fast rate, but we are talking to it. Yeah, so pretty amazing. Right, now, that's basically the combination, the talk I wanted to give. But now I wanted to do was to do a little demonstration. Now, I don't know if your friend is around.
Nada.
No, yeah, I just need her to switch.
She's just outside. Just outside. Yeah.
Yeah, that's great. Which is started. Now, in order for this to work, we're going to need an outer loop. And as luck would have it, here is one here.
I've done it in years.
No, that's okay. What you have to do is hold that up. Now, that's just an ordinary amber radio. We're going to do a little test today. I can't communicate with this light because we're just not bring a ground signal and have a satellite turn on the queue and do that. So what we're going to do is do a little experiment here. That's great, thank you. That's great, I think we're right now. Yeah. What we're going to do is do a little experiment here. And what I've got is our friend, the software-defined radio. And we have a whole series of terminals on the end here, 2 transmit and 2 receive. I'm going to only use one pair. We've got one antenna here and another antenna here. We're going to receive a signal, change the frequency in real time, and retransmit it. And in order to do this, I'm going to have to demonstrate, if this works.
By the way, though, it's not the shot when you think about what you do.
Yeah, I realise that. Yeah, folks at home can't see this. Sorry about that.
I can put my camera.
Yeah, maybe you should use your.
Okay. Now, you might have guessed that in order to do all these things, there needs to be a fair bit of software. In the modern world, we don't necessarily write that software the old-fashioned way. We write it using a software development environment, and for the purposes of radio, there's a special software development environment called GNU Radio, funny name, that does all this for us. Okay, and I'm going to try and get this working now. When I first started doing this for Eagle, we did this before one of the spacecraft. I had never even operated this. So it was quite a job to learn it, but I did. And had a lot of help from Jude, obviously, but a couple of others also. Now, let me explain what we've got here. Normally with spacecraft, and normally with software, you write the software in a series of groups called subroutines. Okay? Each of these subroutines are represented here by those blocks that you see there. Okay, I'll just briefly go through them.
Go get Nada.
Because it's not, see, that computer's not on Zoom. So we can see it here, but nobody else can see it. I don't know, there's not much else we can do.
Not a lot.
No.
We could do that. I don't know if they'll see too much. I don't know if they'll see too much, but we'll
So
do
you
it.
tell them if they look at Ann and Eva's screen,
Yeah.
they can sort of see what
Sort
you're
of see
doing.
what's going on. Now, what we've got is a series of blocks. The first of them connects the software-defined radio head to the computer, which is here. We then do a little bit of stuff called rational resampling. It's changing the sampling rate. The initial sampling rate is 4 megabytes, 4 megahertz. So it's pretty fast. We go through a series of resamplings, a filter, then we receive it in FM, then we resample the audio signal, and then we transmit it again to the wideband transmit, resample it again upwards, so we upsample it, having downsampled it before, we now upsample it, and we send it to another connection which connects to this again, but now to the output, to the transmit side. Okay, so keep your fingers crossed. What I'm now going to do is run that. And if it goes right,
I can't see any of this.
You need to, I'm trying to show it on my screen, but it's.
what you'll notice is, if you can hold that up, is that that's now receiving a signal from the ABC. It should not be able to do that. That's an angel radio. It's receiving at 92.9 megahertz. That's ABC FM. Sorry for the folks that don't know this. It's receiving this signal here at the bottom and transmitting that signal there at the top. So it's just picking out one signal. If I want to change that, I can just change this. Pick out that. Pick out the next signal. Further. Now I've changed the channel. So David changed it very accurately. Now I'm a little bit off. Okay.
Seeing nothing.
Ian, you have to look at a different. It's a computer we can't share. If you, I'm pointing my camera at it.
The screen's too bright and we can't make any on it, out on it.
No, it's.
My suggestion is you stop sharing, Tony, and maybe the others see the rest of it.
Okay, so that worked all right for the people in the room, but it didn't work very well for the people outside the room. Sorry about that. We'll unshare this.
Because basically you can't see anything else when you've got the presentation on.
Yeah.
As soon as you stop that, we might be able to do something else with the cameras.
So
My computer's still showing the previous computers.
okay.
That's Lizzie's in presentation.
Sharing. Yeah, thanks for that. That'd be great. Okay. All right. So that didn't go exactly as I'd have hoped it would have gone, but it allows us at least to show that some of the processing, the way that you operate a computer, a software-defined radio involves mostly software and very little of the hardware. Now, if I'm finished with that, I just close that because I don't need that anymore. So I've now developed the software. And so
Wayne, if you point your computer towards the Tony's screen, I could see it then.
yeah, that's a thought.
Is it okay now?
That's better.
Fine, that's no problem. Yeah, probably got a better camera than everyone else has too.
Now, if I just run the software like that, without the software development environment,
It's not real good, but it gives us an idea.
yeah, that will now, well, it's not very audible.
And your direct view is too bright.
Yeah.
The cameras, you're getting a lot of reflections from the screen, so there's a lot of light.
Yes.
Yeah, so Wayne's shows it better from an angle.
We can slightly move the screen up too.
Okay, well, that's all right. What we'll do is shut it down. That works very well. That works very well. Oh, that's the wrong one. That's why. Sorry about that.
So basically Tony's running some computer software to generate those signals.
Yeah, that's right.
That's what he's coming up with in a second. That's actually the program running at the moment. As you can see, it's coming up there. It's in Python, isn't it, Tony?
Yeah. Sorry about this, I've just got to.
Python's not compatible with Zoom.
No, that's right.
No, it's a fairly common AI language. People use.
I'm gonna run that again to make sure I've got the correct, FMRX. I'm sorry, wrong one. Okay, right. That code that was created by the software development environment, by the new radio. I now no longer need the software development environment. The software runs. So that's how you run the ground switch. It's not turning it off. Right. That didn't go as well as I'd hoped, but it illustrates the point that the modern communication systems use software-defined radio, which is 70% software and 30% radio. That's really what it goes to it. Okay, thanks for listening, everyone.
Questions? Try and put them in the chat. We might be able to go back and show them the environment again. So let's not give up completely on that.
Well, we could share, if Tony, if you go to where you can see everybody, the Brady Bunch up on the screen, can you share that computer up there?
Yeah.
Then if we can see everybody up there, then the people at home can at least ask questions and you can see them.
I see, got right. Okay. All right, good. I just.
Why?
Chat.
This chat. Why can't we see everybody?
They're all there, just.
No, there's actually 9 of them, not just 4 of them.
Okay. Yeah, that's right.
I'm on a train coming home from the city.
That's good.
So I'm on my
There we
iPad.
go.
It's all a bit much for me, so I can't ask you questions, but it gives me an idea of how complicated things are done.
All right.
So we can see you all on the screen now. If you want to turn your cameras on, we can at least say wave to you.
I'd love to have brought up the flow diagram for you, but I have to do it on a different computer.
Yeah. It's one problem.
All right. So if anyone's got any other questions, fire them away. And we'll, without the flow diagram, we'll at least see what we can do to answer them for you. I think so. All right. Well,
I got
yes.
just a broad question.
Yes.
This train will stop at Stratfield.
So you've painted a picture today,
Yeah.
Tony, of the digital world has made all this possible.
Yes. Yes.
So were it not the digital world, could we communicate using old analog radio waves with spacecraft?
Yes, you can,
Yeah.
but you would need a piece of equipment that would have trouble fitting in this room.
Right,
As opposed to that.
right. Because of the power.
Just the power requirements and just the space needed to fit everything in. Okay, now this is all highly integrated circuitry.
There's tiny.
Tiny little things, yeah. And low power.
Yep.
And relatively cheap. For example, that you could land that in Australia for under $900. Now, the ground station that the guys want to sell us, want to sell private people is all hundreds of thousands of dollars. Right? With a bit of work, you can do some fairly amazing things just by building it in software.
Right.
As opposed to just having massive equipment to lots of money, really cubic money, huge amounts of money, to build that kind of thing. And an army of engineers to take care of it.
So the next part of the question then touches on what you said earlier on.
Yeah.
You know, we know that the low Earth orbit is absolutely cluttered with tens of thousands of devices.
Yes, it is.
So is there still spectrum available for communication?
There's huge pressure on the spectrum, massive pressure on the spectrum.
Right.
I don't know how they fit it all in, I'm going to be honest with you.
Okay.
But they've got to deal with fairly low bandwidth transmission, and with high enough data, they're squeezing the data into low bandwidth, which allows you to have enough spectrum to fuel the spacecraft, which is a real challenge. And that's the real ongoing challenge at the moment.
So are there international protocols that have been developed?
Massively complicated protocols. And we
Okay.
went through this with the amateur stuff with the
Right.
It takes the best part of 18 months to get yourself through. And then the forms you've got to fill out are unbelievable. It's torture.
Yeah.
And you're on, especially where amateur is concerned, it's almost goodwill. If you don't have goodwill with them, you just don't get it.
Right.
And that happens with us. And we sort of ran out of goodwill with them.
Yeah.
And they were good to us for a while, and then we said, okay, enough now. And they didn't give us any more in the amateur band anyway.
So the frequencies that are allocated for various uses around the world,
Yes.
like commercial radio
Yes.
or satellites or police or whatever,
Yeah.
are those frequency bands sort of old-fashioned, if you like? They were designed for a period of 60 to 70?
If they were still used in the way that they were originally assigned in the 60s or 70s, yes. But the model, the pattern, the map of frequencies now is terrifying. If I were to bring the poster in and show you, you'd have to get a microscope to get up to it to be able to see all the detail.
Because I know over the decades, people have been moved out of bandwidths to make room.
Yeah, in and out all over the place. And the other thing that really has an effect, I don't have an example of it here, but it's something like that. That's a radio transmitter. What they call it a low interference potential emitter, for sure. Okay. But there's an assigned band. Technically, what I was doing then, just at a few milliwatts of power, was transmitting in an amateur band, which technically I'm not supposed to do because it was music. I'm not supposed to transmit music on it. The signal wouldn't get out of this room, so I can get away with that. So that's how we operate.
So are they actually, because like a university satellite doesn't have the money to spend hundreds of thousands. So are you guys, that's kind of what you're building, is a ground station with
Like that, yeah.
Yeah, so-
with an amplifier on the front of it.
an affordable ground station?
Yeah. And so I guess that if you take the labor out of it, it's a few tens of thousands of dollars. Whereas if they want to sell you a commercial one, it's a minimum of $100,000.
You still have to know how to work it.
And you still have to know how to run it. Yeah, that's right. You have to be a competent operator. Okay.
One more question.
Yes.
Is there any part of the electromagnetic spectrum at either end of the
Yes.
the useful radio spectrum that is being explored now as a means of broadening this thing?
Oh, constantly being reassessed. There's meetings going on all over the world. The International Amateur Radio Union, the International Radio Transmission. I can't remember.
Yep.
The ACMA runs the Australian arm of that, which they're kind of our signatories to the world, and except for the amateur stuff, and that's done through whoever takes it on, like me here, or we deal with the International Amateur Radio Union, and that's a group that meets from all over the world every few weeks. We deal with them if we have to deal with them. We did for a while. So yes, there's a huge international coordination. From time to time, you get ethics, as they call them. Eva's got a band for the spacecraft, and they get little communications from other users who might conceivably be more near the band.
Yeah.
No, a lot of it is grandstanding
Yes.
and yes, people trying to say how important they are. And it's partly a matter of just wanting to make it difficult for other people to use. So you have groups who read your license application, and they know perfectly well that you say that you're only going to use the, let's say, the S-band over Australia, but they'll go and put in a complaint that you're going to use it over Germany or the United States. And it's really because they want you to have to spend money on lawyers or an expert to argue with.
So usually an engineer.
It's very frustrating because, and you have others who basically just say, we've got a satellite, it's within a factor of 2 of your frequency. When, you know, you're at 146 megahertz or something, your bandwidth that you're allowed is 30 kilohertz. And, you know, they're a factor of 2 away. There's no way you're going to be
assuming your equipment is well built.
Yeah. So it's grandstanding. And it's often the groups that either have lots and lots of assets or they have almost none.
One of the other things we need to do is when we deal with a frequency band, we look at, we have to be concerned with exact multiples of that band, because if we produce spurious output harmonics, they'll appear in those bands, but not all of the others. So it's another thing to consider. All right.
So,
I was just going to ask something related to the previous question.
Yeah.
With mobile phones,
Yes.
you're going, you know, G3, G4, G5, G6.
Yeah.
Is someone being bumped out of the way to make room for G6?
Probably they will. Although, but G6 is a long way up the spectrum.
It is.
It's hard to generate frequencies. See, that thing can produce radio up to 6 gigahertz, and that's it. And when you get beyond that, you can't rely on wires and tracks and boards anymore. You've got to have little waveguides. That gets to be very difficult to do, to convert the signal, to be able to move the signal around at those frequencies. You can't rely on metal. If we were dealing at those frequencies, that radio would have to be almost up against the antenna, because we couldn't transmit the signal through that much wire. It would just be attenuated.
Or a certain amount of air. Yes.
A certain amount of
It depends on the situation. But often I think they've actually, the ITU has gone ahead and allocated bands, you know, well up into 60 gigahertz and above, well in advance. I mean, it's now allocated. And now what will happen is that people are now moving into those bands, because at higher frequencies, you can transmit more data in a given amount of time.
Yeah.
Because basically your characteristic time is 1 over the frequency.
But not for such a long distance and through trees and buildings.
As long as it's only free space that you've got to transmit through, you're okay.
No, it depends on the frequencies, because at certain frequencies, let's say between, from memory, 50 and 60 gigahertz, in that range, you get a lot of absorption by ozone, for instance. So if you're trying to transmit from space to the ground, well, it's not going to happen. But if you do it at 20 gigahertz or at 6 and so on, there's windows, so to speak, so gaps in the absorbance.
Okay.
And so that's where people tend to try and do satellite to ground. Whereas, you know, the range 50 to 60 gigahertz is great if it's satellite to satellite, because then you're not going through the atmosphere. You don't care about the ozone absorption.
So with the software side of things, are you able to look at, say, use a similar frequency or the same frequency that using encryption layering?
So that's more complicated. I don't know. I can't tell you much about that. So I don't know much about it. You can certainly multiplex your encryption. I don't know how you would do that using equipment this simple.
No.
Obviously pretty simple. You were asking actually about the upper limit, the limits of the band. They're going up in the millimeter waves now, in the 200, 250 gigahertz range. experimenting with that, they're not using it. But they've got to get up to there if we're going to get away with all this the pressure we've got in the spectrum.
Yeah, because
Ian's got a
Ian's got a
question.
question.
You've got a
Ian,
second.
yes, sorry.
Ian,
Oh,
can
thank you.
you,
Yes,
we can hear
I
you.
can. Can you? Yes, can you hear me now?
Yes,
Yes.
yeah.
Okay, that's great. Yes, thanks for the great talk. I was in the trade back in the 1980s when I worked for OSAT, which became Optus long ago, if anyone remembers that. And one thing we did as an exercise, we had a radio amateur in Adelaide called Des Clift. Tony, did you ever know of Des Clift? I forget his call sign.
I don't know that individual, but I know quite a few of the people who worked in OSAT. You'd have dealt with Gordon Pike and a few others.
That's correct. Yes. Another one was Graham Ratcliffe, who was an amateur in Sydney. I can't know his call
The
either.
one that I know best is Tony Hutchinson or Shane Lind, but you might not know.
Anyway, one thing we did as an exercise, we had our brand new shiny satellites up there in geostationary orbit, beaming their signals down to 36,000 kilometres. And an amateur made us some little horn antennas, 5 centimetres by 5 centimetres, going to coax cable. And we managed to receive the beacon from one of the Optus satellites from 36,000 kilometres away using this tiny little horn.
Did the spacecraft have a directional antenna on it? I think it did.
Yes, of course, yes.
So
yes.
what's happened there is that you picked up a lot of gain at the spacecraft end because of the antenna.
Anyway, that was considered quite an achievement, but they had to track the Doppler because the satellite wobbles a bit in its orbit, and they had to have very narrow band filter, some hertz wide, so they had to track the signal to get a consistency.
Yeah, that's true. The Doppler shift, though, at that altitude is virtually nothing because it's geostationary. It's not moving with respect to the ground.
Yes, so we were using 10 gigahertz and 12 gigahertz for the uplink and downlink.
That's right.
In those days, and the OSAT or Optus station is still there at Belrose. You can drive past it. You can't go in without a lot of rigmarole, but it's still there. And I visited the other day, so that was good fun.
I've been past it many times. Yeah, I know some of the people who used to work there.
Great.
All right, thanks for that. Any other questions?
I just have one, and that was to do with the, you said that early on you didn't have as much problem asking the amateurs for uses. Is that because there were only a few
No,
CubeSat
it's
trying to,
because we sort of kept going back to the well and we lost goodwill.
But there's also a lot more people asking.
And there's more pressure on the spectrum, but also there was a fellow working with Eva who wanted some really incredible requirements way up in any gig, and then we didn't use them because he couldn't deliver what he said he was going to do in Paris, of course. And that left them not liking us so much, so they were less willing to help us.
From my understanding, actually, it was the Australians who were positive.
Oh, they were very positive.
The internationals who
internationals
creeps.
No, they were just totally sick of us, that's all.
No creeps.
Yeah. Okay. All yours, mate.
Thank you, Tony.
Okay.